Let's continue our discussion of matrix rank. So go ahead and kick off your Python session. We'll open this up. Okay, so if you remember from last time, we were talking about matrix rank. And specifically, we said that the rank of a matrix is the dimension of the span of its columns. And we also talked about null space, which is the set of vectors that that matrix maps to zero. In other words, it's the set of weights that you can use to linearly combine the columns of the matrix to get the zero vector. And we talked about how the dimension of the null space trades off against the dimension of the range or the rank. And I want to ask just a short review question from last time to see whether folks are feeling comfortable with that. So suppose that the null space of a 10 by 5 matrix A is 2. What is the rank of A? So the rank should be 3. Right, and that's because, as we learned last time, the rank plus the nullity of a matrix is equal to its number of columns. The idea is that if the columns were linearly independent, the rank would be equal to the number of columns, because it's how many vectors you have, and they're linearly independent. And the nullity would be 0, because only the 0 vector would linearly combine those columns to give 0. That's what it means for them to be linearly independent. So the rank plus the nullity equals the number of columns if it's full rank. And then also, even if it's not, because if you want to trade down where you lose some dimensions in your range, you have to do that by mapping some vectors to 0, and the dimensions track one another. Every time you lose a dimension on the range side, you gain a dimension on the null space side. Okay, so here's another one. Find the dimension of the null space of the matrix A defined in this code. Oh, people are computing it. Everyone's computing it using the function that they know. I was thinking this would be more of an inspection problem, but computing it explicitly is also an option. All right, nice job. So folks settled in on this one. A couple of incorrect answers, but then people kind of came around. So that was a good thing to work through. So what's going on here? We can just look at this matrix printed out right here. What's going on is that the first 4 columns are very likely to be, because they're randomly generated, it's very unlikely you're going to have sort of accidental linear dependencies here. So the first 4 columns are going to be linearly independent, very likely. But then this 5th column, in that case, cannot be. It must be in the span of these first 4, because the dimension of R4 is 4. We already have a linearly independent set of 4 vectors in R4 here. It necessarily fills up the space, assuming they are indeed linearly independent, which means these last 3 are all going to be some linear combination of the first 4. So the rank is equal to 4, and the number of columns is equal to 7. Therefore, the nullity has to be 7 minus 4, or 3. So last time when we did this, we sort of manually introduced linear dependencies to get this effect where some columns are linear combinations of other ones. This time we did it by choosing a matrix which is wider than it is tall. So that will force some vectors to be linear combinations of others. All right, so as some folks used on that particular problem, the scipy.lineage.nullspace function returns a matrix whose columns are linearly independent elements of the null space. And so this question is, what happens if we multiply that matrix that is returned by this function? What if we multiply that by null space of A @ null space of A? You could do it, but you can also think about conceptually, what does it have to be? All right, so I'll get Nick to talk about his answer. Yeah, that's exactly what's going on. We're going to get a matrix of all zeros. And here's the reason. When you multiply, as Nick was explaining, if you multiply a matrix by another matrix that here I've split out into its columns. So the idea is this is notation for a matrix whose first column is x1, whose second column is x2, third column is x3. Let's just say there are 3 columns for simplicity. When you multiply a matrix by another matrix, one way to think about what happens, there are several ways to think about it, but one way is to think about A multiplying by each of the columns, and then the resulting columns get reassembled into a matrix over here. So once you understand the matrix vector product, the matrix product follows from that just by column-wise, considering each product separately. So the point is, if the columns of the matrix returned by the null space function are supposed to be in the null space of A, that means A maps each one of them to the 0 vector. So we're going to get the 0 vector in each column over here. So in other words, we're going to get a 0 matrix. So we can run this and check this works out. By the way, I used the all close function here instead of just multiplying this out, because if you multiply it out, it sort of looks funky. We have this, 7.5 times 10 to the minus 16 and so on. So this is a very common thing when you're checking stuff using numerical computation. So all this is numerical, especially this null space part right here, the way that computation works, which we're going to learn about later when we actually get into data 1010. The way this computation works, it will almost always introduce numerical error, even if you have integer entries in your matrix. So in any case, it can be a little annoying to run some code like this and then try to just inspect, are they all zeros? Because it takes a second to kind of look around. But you can use the all close function, and that will also work. And this function is designed to sort of know what sorts of errors are kind of appropriate for round off and ignore those. We're also, by the way, in data 1010 going to learn quite a bit about the nature of these round off errors and how you should be thinking about whether they're going to be a problem in a given calculation. Usually they're not, but occasionally they are, and it always makes you a little uneasy. So having a little more knowledge there, I think, is really useful if you're going to be doing scientific computing of any kind extensively in the future. Anyway, here's another question. So explain why the range of the transformation, which maps an input vector x to the output a times x, is the same as the span of the columns of A. Very nice. People are typing out some excellent explanations here. All right, so several really nice explanations here. Let's see. Yeah, so Shabam, you have a check mark. Do you want to talk about your answer here? Great, nice job. So this follows from the definition of the matrix vector product. So A times X is the linear combination of the columns of A with weights given by the entries of X. Therefore, the range of the transformation and the span of the columns are both just everything you can get in the form A times X, where X is just some vector from Rn, if we're saying that M and N are the dimensions of A. So I want to mention another thing because it ties in with one of the homework problems. So this is kind of a surprising fact, maybe the first sort of really surprising fact about linear algebra. Unnecessary linear dependencies among the columns of a matrix are actually matched by unnecessary linear dependencies among the rows. And I mean, if you haven't thought about it too much, maybe it sounds pretty believable, but I think there's really no reason to expect this to be the case. So in other words, what we're saying is the span of the columns and the span of the rows, they're going to be completely different spaces. They're not the same space. They don't even, unless the matrix happens to be square, they don't even live in the same Euclidean space. Like if you have a 4x7 matrix, then the columns live in R4, the rows live in R7, and the vectors are totally different. They have, the same numbers serve as entries, but they fill in totally different places. So like, what should the two have to do with one another? Like, let's say, for example, a 4x6 matrix, it could have rank 4. Remember, we learned that the biggest rank that a matrix can have is just the smaller of its two dimensions. Okay, but let's say we happen to have a matrix which is rank 3. So there's an extra linear dependency among the columns beyond what's implied by the shape of the matrix. So that's fine, but you could totally imagine that once you turn and look at the rows, they're still linearly independent. I mean, there's plenty of space for that. They're in R6. There's only 4 of them. Why not? Like, it's just not clear what the rows and columns really have to do with one another if you look at a particular matrix and just slice it both different ways. But as it turns out, there will, in fact, necessarily have to be a linear dependence among those 4 vectors. And the dimension of the span will also be 3. So there's a very nice proof of this from Mathematics Magazine that I came across a few years ago when I was teaching linear algebra. And I wanted to just briefly discuss it because it touches on an idea that I think is actually super useful in linear algebra in general and data science in particular when you're trying to understand the structure of linear spaces. And I like to call this the dimension bottleneck, which is, it is sort of a generic term for it. I'm sure other people call it that, but it's not a standard term, is what I'm trying to signal. I use this term to be evocative more than to teach you new vocabulary. Okay, but here's the idea. So I'll take a step back for a second. So suppose we're composing two linear transformations from R3 to R3. So we're going to map R3 to R3 somehow, and then all those outputs, we're going to apply some additional transformation to map them to their sort of like final resting location. And suppose further that the first of those two transformations maps the whole 3D space down to a single line through the origin. What shape are we going to get after we apply another transformation beyond that first one and look at the composition of the two transformations? So there were two essential ideas expressed, these first ones and these ones. Several people said either a line or a point, and other people said it'll still be a line. In spirit, these are both kind of right. You can map everything to the origin. So imagine, for example, that the second transformation is the zero transformation, just maps everything in R3 to the origin. Then definitely you could get just a point. You could also get a line. That's sort of the general situation. If you just pick random transformations, very likely you're going to get a line after you initially map R3 down to a line, then map that line to R3 again with a linear transformation generically, you're going to end up with another line. The important thing here, though, which everyone got right, is that you definitely are not going to get a plane or the whole three-dimensional space back. So conceptually, it's sort of clear that that should be the case, because, you know, think about what you would have to do to take a line and somehow morph it so that it fills up the plane or three-dimensional space. It's a really crazy operation to try to think about. It actually can be done. So there's a really beautiful 3 Blue 1 Brown video on not only this idea of a curve that can fill up space, but also how that piece of sort of, in one sense, kind of exotic mathematics actually touches on some very practical real life ideas that are interesting in their own right. Highly recommend that video. But anyway, the point is you have to do something crazy, definitely not linear, like way not linear, to take a low dimensional space and somehow, you know, crinkle it up and get it to fill up a higher dimensional space. So linear transformations are not going to do that. So that means that compositions of linear maps have a sort of only as strong as your weakest link behavior when it comes to rank. If you have one map in a chain of compositions that's low rank, then the whole composition will necessarily also be low rank. You have to stay high throughout the whole chain if you want a composition to have high rank. All right, once you lose dimensions, you never get them back. So here it is in the form of a mathlet. So I want to try to bring this idea to life. So this is maybe one of the more complex mathlets. So it requires a little bit of explanation, but the idea is that these green and purple vectors are telling you what the two matrices are. So notice I have this slider for the middle one, for this first map from here to here, set to 0. So this isn't being applied. This grid is just the same input grid here. And that way you can see the action of B. So in this case, B maps the first standard basis vector to 1, 0. That's the green one there. The second one to -1, +1. So it's a shear transformation that tilts to the left. And so that's B. And if we want to visualize A, we can just move this slider over. You can see that it's a shear with a tilt to the right. So that's A and B. And then if we want to visualize the whole composition, we can just put both sliders all the way to the right. So both maps are being fully applied. And in fact, these two matrices happen to be inverses of one another. So if you shear once to the right and then shear to the left by the same amount, then you get back to nothing. This is just the identity matrix. But you can move this around. So let's say we want to make the second transformation like the first. So they both shear to the right. So this grid, it looks the same as this one is going to look when I slide this over. Now we can see the composition over here, and it's what you would expect. It shears to the right and then shears to the right some more. So we just get a more pronounced shearing action to the right here. So this mathlet is a generic tool for visualizing compositions of transformations from R2 to R2. So this can be useful for all sorts of situations where you might be wanting to think about transformations from R2 to R2. All right, so what's the use case for this particular context? we want to say that if we choose a rank 1 matrix, like this one we talked about last time, then whatever you do over here, you're definitely only going to get a line. All of these different configurations of the green and purple are just giving you a line, except occasionally we can see that line collapsing down to a single point. Where was one of those instances where we saw that? It's funny. It happened a minute ago. I'm not trying to use any math intuition here. I'm just grabbing the mathlet and trying to, yeah, there we go. That seems to, well, not quite. Whatever. There we go. That one did it. Yeah. So you can make this line collapse down to a single point if you work hard enough at it. But clearly you're not getting your grid back. Once this is a line, that's it. Okay. So anyway, this proof that's in the homework, it relies on this particular insight. In fact, this is kind of the crux of the idea. So given an n by n matrix, and here's the, who'd have thought of this? This is the step that you get handed as the learner to say, like, start with this and see what you can do with it. So here's what we do. We define R to be the smallest positive integer such that A can be written as a matrix product B times C, where B is m by R and C is R by n. So in other words, we're bottlenecking the matrix A through the smallest intermediate space as possible. So the smallest dimensional space here in the middle. So the idea is like maybe this initial input is like R10 and this output is R8, but maybe it's possible to write the whole transformation as something that goes through like R3 here in the middle. So you're able to squeeze it down to a 3D space. And then there's some other transformation that kind of takes that 3D space and appropriately positions it over here where the range actually is. So the idea is like, you want to make this as tight as possible. If it happens to be, let's say 3, then you'd want to actually use R3, not like R4 or some higher space. You can't squeeze it any more than the actual rank, because as we just saw, if the whole thing was like rank 5, you couldn't possibly squeeze it through R3, because just like here, you wouldn't be able to get R5 back, or a 5-dimensional range back in the output. All right, so just saying that in a message here. So this weakest link observation that we made tells us that the rank of the matrix can be no larger than this value R that we come up with in this initial, like, really cool step. But because the R is chosen to be as small as possible, we can show the rank is actually exactly equal to R. And then you can, from there, turn that argument around and basically use the same idea to show that the row rank is also equal to R, the same R that comes from this process, this exact same process here. So I don't want to go further into the details of that argument because it's in the assignment and I want to leave you to work through it. But also I anticipate that if I don't give that some introduction, then that might be a little bit of a difficult cliff when you first read that problem statement to kind of see what's going on. All right, so the last kind of section of the linear algebra course we're going to do is on orthogonality. And what we're going to see is that orthogonality is kind of like linear independence on steroids. So linear independence kind of makes sure that vectors don't do completely awful things, but orthogonality is going to ensure that they do very nice things. That's kind of the idea, and we'll work up to that. And all of the kind of coolest stuff for numerical linear algebra as applied to all sorts of applications or sort of applied math contexts, including data science. It's at least the stuff that we develop in this program, it's all going to flow through this idea. So this is going to be really critical for the kind of really fun punchline that we end up at in Data 1010. So, okay, so here's a section on orthogonality. Here's kind of my initial pitch. So pure linear algebra only deals with vector addition and scalar multiplication. In some sense, the idea is how far can we go thinking only about vector addition and scalar multiplication and ideas that flow from that. So all of this rank and nullity stuff, it all comes back to those two operations. We never used other operations besides those. But in Rn, we do have additional geometric structure beyond just those two things. We have the idea of angle. So I can put two vectors in the plane and I can ask, what's the angle between them? So you know what an angle looks like. And in some sense, this figure is redundant, but whatever. This would put the mental image in your mind. We're going to be curious about working out what is this angle between these two vectors. I'm assuming that you've seen some of this before in the pre-reading or in previous courses. So I want to ask to kind of see where folks are right now. What can we do with the coordinates of two vectors, like say these two vectors, to find this angle in between them? Great. So I'd like to hear from Manlin, whose answer I've shared here. Very good. Yeah, that's exactly right. So here's the key point. So we compute the dot product, which is introduced in the pre-reading. And that's going to give us information about the angle between the two vectors. And the way the dot product works, so I'm sure you've seen this, but just to review, the way the dot product works is you just multiply corresponding entries and add. So like here we have 1 multiplies by 1 and 2 multiplies by a half. And so that adds up to 2. So the dot product of these two vectors shown in the figure, which are supposed to be 1 comma a half and 1 comma 2, the dot product is 2. And the dot product, as Manlin was just explaining, is related to the cosine of the angle between two vectors. This is maybe worth thinking about to kind of help you remember how the formula works. So you can tell from the definition of the dot product that it doesn't give you totally direct information about the angle. There's a little something else mixed in there. And here's how you can tell. So suppose we scale one of the vectors by a factor of 5 while leaving the other vector the same. Then what happens to the angle in the dot product after we do that scaling by a factor of 5? Okay, so the way it works out here, in the context of this question, what we can see is that the angle stays the same, of course, because you're not changing anything about the angle between the two vectors, while as the dot product multiplies by a factor of 5, because each term in this sum that determines the value of the dot product is going to pick up an extra factor of 5. So by the distributive property of multiplication over addition, the dot product also has that property. Now, the way that you can deal with that is by dividing by the lengths of the vectors after you compute the dot product. So sort of a normalized dot product. So it's whatever the dot product works out to divided by the product of the norms of the two vectors. And that way, if you scale one of the vectors by a certain factor, the top is going to pick up that extra factor, but so is the bottom, and that those extra contributions cancel. So that's a scale invariant quantity, at least. It could tell us something about the angle. And in fact, it does. So this value that you get when you divide the dot product by the products of the norms of these vectors. So this is, tails at the origin, heads at 1 comma 2. So this is a square root of 5 norm vector. And this one happens to be square root of 5 over 2. So when you divide the dot product by the product of these two lengths, you get some number. And as it turns out, this number will necessarily be between -1 and 1. And in fact, it tells us the cosine of the angle in between the two vectors. So it's supposed to be the cosine of that angle there. And we can compute the inverse cosine of, let's say, for this particular problem, 0.8 to see what the angle should be. And we get 36.87 degrees, something like that. And that seems legit. If you eyeball this and someone tells you it's 37 degrees, you should probably believe them, because it's certainly not obviously different from that. And in fact, this is a correct answer here. So I'm going to skip over explaining why that's the case, but just to be clear, this is why the dot product is powerful. So the dot product has two different properties at once. It has this really simple computational formula, and also at the same time, it has this nice geometric property that the dot product tells you directly what the sort of rescaled dot product tells you directly what the cosine of the angle between the two vectors is. So that's great. It has a good geometric interpretation, gives you useful information, and it's also really easy to compute. So that's why we do that instead of trigonometry. Let's say like law of cosines, that sort of stuff. So things from like a trig class in high school. You certainly can do that. It's equivalent ultimately, but this is a tidier way to repackage it. So a couple of really important algebraic properties of the dot product are that a vector dotted with itself is just the squared norm of that vector. There we go. So it came through eventually. Yeah, so anyway, back to here. The dot products, it has these two key properties. So dotting a vector with itself gives a squared length of that vector. That's just directly from the definition. Multiply in pairs and add up. What do you get if you do that with a vector and itself? It's going to be the same thing as if you ask what's the squared norm of that vector. And it's also linear. This one is maybe a little less obvious geometrically, but if you have some linear operation, something involving scalar addition, something involving vector addition or scalar multiplication or some combination thereof, you can distribute a dot product across that operation and it will be always valid. So we're going to put that to use in a little bit. Rather than building in exercises here for that, we're just going to circle back to it when it's actually going to be really useful to us. But if you are concerned about either of these properties, you can just work out both sides in terms of components and see that they are the same thing. So it's just kind of follows from the definition. There's not something tricky to show. It's just a little dry. So we're going to skip it. All right. So the most important angle is 90 degrees. You'd be interested in other angles in other situations. Like as Manlin was talking about, you have cosine similarity, which is an idea that shows up in machine learning contexts. But fundamentally, 90-degree angles are really, really great. And so they're going to warrant quite a bit of our attention compared to other angles. And we'll have lots of terms for it accordingly. So we can say the vectors are orthogonal or perpendicular, or that they have a dot product of 0. And there are other terms that people use that you'll encounter. They're just all synonyms for each other. They mean that the two vectors meet at a right angle. So just to kind of warm up a little bit, I want you to think about, is orthogonality transitive? In other words, if I have one vector that's orthogonal to a second one, and that second vector is orthogonal to a third vector, does it follow that the first vector is orthogonal to the third? Okay, so just one thing I see showing up in the answers here that I want to address. Well, first, just the answer, and then I'll elaborate. So the answer is no. So for example, you could take any two orthogonal vectors and set the third vector equal to the first one. So let's just say W is equal to U. Then the condition is satisfied because both orthogonality statements are in fact the same statement. But U is not orthogonal to W because it's actually the same vector. Now, several people said it depends. And that is not correct for the following structural reason that you'll see in many instances. So transitivity and in general mathematical properties that are qualified by saying that they work always are not the sort of thing where it depends is a possible answer. So either the property is transitive, the statement in question, in this case, this one, holds all the time, or there exists some instances where it doesn't hold, in which case the assertion of transitivity is false. So if I say for all u, v, and w, we have the following, and in fact, there is a u, v, and w where the statement doesn't hold, then my statement is wrong. It's not sometimes right, it's flat wrong because I made the claim that it works all the time, and it didn't work all the time. So properties like transitivity, they're qualified with for all statements, and therefore they have to be either true or false. Okay, so in any case, there's a lesson to draw here, which is that orthogonality is fundamentally a pairwise property. If I take two vectors, I can say, is this vector orthogonal to this vector? And I can't sort of like chain that in some way. If I have a bunch of vectors and I want sort of maximal orthogonality, as much as orthogonality as I could hope for, what I need to insist is that any pair of distinct vectors from that list, if you take those two vectors and check the angle between them, you get 90 degrees. Or in other words, if you dot them together, you get 0. And we call such a list pairwise orthogonal. So here's an example in R3 of a pairwise orthogonal list of vectors. So you can only have 3 of them, which geometrically I think seems pretty clear. But we'll see why that's the case in a minute. If you look at any 2 of these, they're going to meet at a right angle. So you look straight down where the third one kind of disappears, and you're going to get a 90-degree angle. So this is the idea I want you to have in your mind. This sort of like I do it with my fingers like this, a pairwise orthogonal list of vectors. This is what it's supposed to look like, right? And maybe it's in higher dimensions, so you can't really draw a picture, but still you can imagine this lower dimensional setting to draw intuition from. So one thing that I think makes total sense conceptually is that pairwise orthogonality is a stronger condition than linear independence. You look at these 3 vectors and someone's like, are they linearly independent? You're going to be like, definitely. There's they fail very badly to introduce some linear independence. To introduce some linear dependency between the vectors. Like, not only is this orange one not in the direction of the purple one, it's as far as it could get from being along the purple line. And same thing for the blue one with respect to the plane spanned by the purple and the gold one. You're definitely not linearly dependent here. And in fact, you can show this, and it's really enlightening. So I'll probably give you a little less time than this so we can get to a good punchline by the end of the hour. But suppose that Vn is a non-zero vector, which is perpendicular to all the vectors that came before it in the list from V1 up to Vn. So how can we show that Vn is not in the span of those previous vectors? It kind of should be easy in some sense. It's perpendicular to all of them. So how could it be in the span? But still, we need to explain why this is the case, so we're sure that we're not in some instance where our intuition is breaking down on us for some reason. Yeah, so here's how it works. So some folks were on the right track with that. Lots of folks had ideas that are along the right lines. This one really hits the nail on the head, though. If we want to talk about Vn being in the span or not in the span of V1 up to Vn minus 1, the equation we want to think about is Vn equals C1 V1 plus C2 V2 and so on up to Cn minus 1 Vn minus 1 for some coefficient C1 up to Cn minus 1. So let's put that equation down. So what we're going to do is dot both sides of the equation with Vn. This is where the magic happens. So here we're just writing down the concept of Vn being in the span of these other vectors. What does that look like as an equation? Here we've just written that down. But the next step, which is where something interesting happens, is that we dot both sides of the equation with Vn. And we're going to use both of these properties that we listed earlier. We find that on the left-hand side, we have Vn dotted with itself, which we said was the squared norm of Vn. And on the right-hand side, we can go ahead and distribute the dot product, and we're going to have Vn dotting with all these other Vs. And as we assumed up here, Vn is perpendicular to all of them. So it's going to give all of these dot products are going to give 0. So when all the dust is settled on the right-hand side, we're going to get 0. And that's telling us that the only way to be orthogonal to a bunch of vectors and in their span is to actually be the 0 vector. And we assumed up here that, we're trying to find a non-zero vector. 0 vector is not interesting here. So we stipulated that it be non-zero, and here we're at a contradiction. So this confirms the intuition that orthogonality is a stronger notion than linear independence. If a vector is orthogonal to a bunch of other vectors, then it cannot be in the span of those other vectors. So I want to just maybe put out the next couple of messages. We'll actually get into this next time, but I want to kind of show you where we're going next. So we're going to talk about projection, which is in some sense kind of taking a step beyond just checking whether two vectors are orthogonal or not. It's going to enable us to actually find orthogonal vectors that have desirable properties. So here's the picture. So the idea is like you have a vector u in addition to some original vector v, and you're like, well, I don't really like how u and v are not at a right angle to one another. I want to sort of tighten it up and make them, subtract off this part of u that sticks in the direction of v to get it to go, down here so that it is orthogonal to v. But otherwise, I, want to make it as minimal of a disruption as possible. And that's how you get this vector, which we're calling u perp here. So this is perpendicular symbol serving as a superscript. It's just a name. And we're saying this is the orthogonal component of u. It's the sort of part of u that's sticking in the direction perpendicular to v. And you can play with this figure. Both of these things can be moved. And you can see that u perp always stays perpendicular to v. And it's always, on this parallel line that runs in the direction of v. That parallel line can capture both the head of u, the original vector, and u perp. Anyway, that's what we're going to talk about next time.